Good morning. Today I'm going to be talking to you about 9-4, which is going to be polar arc length and vector basics. If you're in AP Physics, the vector basics part of this should be very, very easy. If you've never seen a vector before in your life, I think this is everything you need for calculus of vectors. But if you're mystified by anything, again, as always, please come and talk to me about this. Do not just assume that you watched the video once and you had a lot of questions, but oh well. One way to see if you understood the video is to do the homework. So make sure you're doing the lesson homework. Make sure you go home and do 9-4, or make sure you're doing 9-4 right now. The first thing is to find the arc length from 0 to 2 pi for this curve. So honestly, it's just going to be a formula. I'm just going to use the formula really here. So I know the bounds of the formula. They told me to go from 0 to 2 pi. And it would be lovely if you guys labeled your equations like arc length, I don't know, square root r squared. This is r. What kind of graph is that? If you said or thought it's a limousin, you are right. And now we're going to have to add the square of its derivative. It's the derivative with respect to theta. Because of how you're used to the other arc length formula, and I'll just write the other one for, I don't know, the other one you use in AB even is 1 plus dy dx squared. So don't get stuck using the slope. Don't think you're using the slope. Don't think you have to find dx, dy, and then divide them. Don't think you have to convert this to an x and y and then divide. That's ridiculous. Instead, we're just taking dr d theta. I'm differentiating with respect to theta. 0, the derivative of 2 is 0. The derivative of cosine is negative sine, so I work it out to get 2 sine theta. So plus 2 sine theta squared dx, and we pull out our calculator and we get to work. Now you don't need to be in polar mode, just to show you what I'm talking about. You can be in, enter. Yeah. Just to show you for sure, you can be in rectangular mode. I'm going to do an integral, math 9. Oh no, this is not the new operating system. That's hilarious. Okay. I'm going to go over how to type this still. I have to ad lib as always, so it's going to be like something like square root. That's funny that I need to find that new operating system, I guess. You want to do 2 minus 2 cosine x. Oh man, it's not even doing it all in one line. Squared, like that. And then plus 2 sine x squared. I forgot a parentheses right there. Oh man, what happened? Anyway, let's see if I can do it right. That closes that parentheses. It's really hard to read, huh? If you're in period 6, this is how JJ lives his life. This is how the old operating system worked. That's why I know how to use it. Oh, I know. You want it with respect to x from 0 to 2 pi. Alright, what happens when we get a nice whole number like that? That is the right answer. Meaning if you don't get that, it's because you typed something wrong. I'm still going to write 16.000. Now, you should be a little suspicious when you get a whole number like that. Maybe it's because you typed something in wrong. Probably not, though. It's probably just a nice classical function is really what's going on. There's probably some nice formula that someone in the 1700s came up with to measure the not circumference, but the perimeter of a figure like that. It's probably related to 4, right? Okay? Make sure you can get 16 when you type that in using your nice operating system. If you didn't watch the last video where this came up, I would be using the thing I do in class, but it doesn't go through. Like, I don't have the microphone and that at the same time. It seems like I can't have both. Oh well. Next. So that's it for polar, is when everyone in class breathed a sigh of relief. The hardest thing about polar will be polar area. For sure. Polar area is the hardest video. Please watch that video. Please make sure you do the homework. That's the hardest thing to understand because it's so goofy. Polar tangent lines are also important, but this is it. It's really 3 things. Polar tangent lines, polar area, and polar arc length. That's all it comes down to. If you can do those 3 types of problems, you're good with polar. And now we finish 9, and we finish all of Calculus BC with some vector definitions. So we're gonna call our vector v. Not call, let's just say. Let v be a vector. That's how a mathematician would write it, and I think that's much more. I'm not saying vector or something else, I'm just going to call it a vector. V is going to be a vector. This is V. Hi, V. Oh, gross. This is a picture of V. So what is a vector? A vector can be called something like, and I'm just going to actually type it. You guys are going to be so impressed. No bold. 30? One definition is a directed line segment. Connell in class called this a ray. Ray. That is right. The more physics definition of it would be it has magnitude, which is strength, and direction. So, classic vector quantities. Since you're not in class, I'm going to make sure you hear this. A vector quantity. Vector quantities. Force. Because I'm pushing something with force, and it has a direction. The way I'm pushing it. Velocity. Acceleration. Right? Oh man. I'm traveling 50 miles an hour north and it has a direction in which you're going. Acceleration, same thing. Those are like the classical examples. I'm not really going to get into it, but like what's something that's not a vector? Not. Position. That's a classical one. Gross. That's like the worst I've ever written position in my life. Oh no. Okay. Sometimes the screen gets finicky. Position. Sometimes my hand gets finicky. Position. Energy is another one. An object just has energy, potential, or kinetic. It doesn't have a direction that energy is being, that energy just doesn't have direction. That's the idea, okay? Why not position? Sorry, I don't know if I said that or got cut off because it was so ugly. Position is a location at a specific time. While the object may be moving, that movement is governed by the velocity. Okay? So position won't be a vector strictly. We might be able to write a vector for its position, and that's where it gets really tricky. But the idea is a vector for a position function would be would be not just a list of its location, but how its location is changing. I guess that's the clearest I could say it. There's a vectorization or a parameterization, and you'll see how this relates to parameters very shortly. So not position in one direction, position in two directions would be. Okay, what else? Magnitude. What is the magnitude? The magnitude would be the size of the vector, in some sense. How many newtons does the force have? What's the speed? Oh, speed's a classic one. We're going to measure magnitude. We're going to say if v is a vector, magnitude will be the double absolute value of v, which we'll say is the square root of x squared plus y squared. This is called modulus, usually. And that should look like Pythagorean theorem. The idea is that this vector has a component form, which we'll get to at the end. The idea of that is, well, if I drop an altitude, that's y, that's x. How long is the vector? X squared plus y. Size, length of vector, direction. I think direction's clear. I don't want to write the formula. The direction of the vector, where it's pointing, can be given by that angle theta. And theta is certainly equal to the arctan, that's usually how we'll define it, of y over x. Because you'll usually be given y over x. You'll usually be given a y component and an x component, and you'll be told to find the direction that vector is traveling in. Equivalent vectors are vectors that have same magnitude and the same direction. And this has to be emphasized in your mind. Not same start or end, not same length. Okay? Those were the two suggestions in class. Those are the two suggestions in class. Not same direction. It has to have the same magnitude and the same direction. Both at the same time. Like, here's a vector with the same size. They're not equal vectors. If a vector is its magnitude, if a vector is defined by magnitude and direction, then for two things to be equal, it has to have the same in both. Here's a vector with the same direction, but not the same size, right? You can see both of those red lines are not what we really want to mean to be the same as this vector. Okay? Component form. The component form of a vector will just be written like this. It's not really a less than sign, but who called it a less than sign in class? It's like an angle bracket. That's what they're really technically called. Just something where normal sized letters can live, not like a less than symbol, which might be more like that. Yeah, it's the same basic shape, but the angle is different, and I don't know. You can't fit X and Y in there. No. So that's the component form. We're going to have a list of the X stuff, then the Y stuff. That's really all I'm going to say. We're going to do an example or three with this, but those are the basics. I mostly need you to know the formulas. That's not really a formula even. But all those formulas can be, brought back from this picture. So if you just know this picture of how a vector can look, you're fine. So here we go. The initial point of a vector is -1, 3. Its terminal point is 2, 7. Graph the vector. Now, depending on how you feel so far, this is a situation where I would recommend pausing the video, trying it out. If you need a hint, you can watch a little bit more, but really you should be able to do all of this on your own, I would imagine. So pause it, come back, 3, 2, 1. Here we go. The initial point, -1, 3. Back to good old rectangular coordinates. Happy, happy, happy. Terminal point, 2, 7. Now, why do they have to tell you initial and terminal? Terminal means final point because vectors have a direction. And that's very important. What else has direction? Parametrics. So the parametric stuff we started the unit with will come full circle in 9.4 and 9.5, especially 9.5. So there's your vector. Graph the vector in standard position on the same axis. So now you might be like, wait, we didn't talk about standard position. Standard position, start at the origin. So if I wanted to move the start to the origin, what kind of a shift would that be? That would be down 1, 2, 3, right 1. And if I move this point down 1, 2, 3, right 1, we're talking about 4, 3. No, 3, 4. Sorry. So that's how we get into standard position. We move the start, the base of the vector, the tail of the vector, to the origin. The component form of that vector is the same as this. So component form, here I go, I would do terminal minus start, comma, no, blah, blah, blah. And now we just plug in the reds. Terminal X. Oh, man. No, not having a day here. The last X. I tried to do the slope formula because, like you guys, I have memorized it all. And it's all rote memory. And it's just playing with fire every time I try to do anything different. Start final X minus initial X. Final Y minus initial Y. That's how we do it. Final X minus initial X, final Y minus initial Y, and the component form is 3, 4. Does that check out? Good. Magnitude of the vector. Or who really couldn't contain himself that day. Squared, x squared plus the y squared inside the square root. It's just the formula that was on the other page. Boom. 5. Direction of the vector. Theta equals arctan of 4/3. Which you have to do in your calculator. You're not going to have this memorized. Mr. Lawrence, our AP physics teacher, tells the people to memorize the angle for a 3, 4, 5 triangle. And that's helpful, but you guys memorize it in degrees. Don't put degrees there. Make sure you can get that in your calculator. Actually, this looks similar. Here we go. This looks normal. Tan inverse. Point. No. Gross. 0.92. Ooh. For the y. Fleet. 4 divided by 3. See? Whether you round or truncate, there's no way to get 928 out of there. That would be marked wrong. Find the direction of this vector. So when they ask you to do this vector, and that's what I mean, now it has a magnitude and direction just by having 2 coordinates. That's what I was trying to say about position earlier. A 2-coordinate position would have a direction toward it, sort of. We'll talk about more of this in P5. When I'm asked to do this, one of the first things I want to consider is that where is our vector living? And this vector lives in this region. -3, somewhere over here, +5. Right? That's the vector. So what's its angle? What is the angle of that vector? That angle, our angles are always drawn toward the x-axis in the counterclockwise direction. That's the angle I'm interested in. Now, I don't know if that helps you guys understand what I'm about to say, but if this is what you did, .030, you're wrong. Not right. Why is it not right? Why does that not give you the right answer? Range tan inverse only in quadrant 1 and quadrant 4. So you must memorize this to do well on this test. I'm going to rewrite this arctan. Arctan only spits out angles in these two quadrants. And this angle is very clearly in quadrant 2. This angle is in quadrant 2, the vector's in quadrant 2, however you want to think about it. You want to be very careful when you're using your inverse trig. And if you're an AB student, if you're in an AB class, let's say, we just talked about this on the day I'm recording it. The angle, you want to be very, very careful which angle you're using, which angle you're giving. So, if I'm talking about an angle in quadrant 2, I want to make sure I really consider that. So negative 1.03 is down here. That's what your tan function is spitting out. That's what arctan is spitting out. Oh, it's down here somewhere. Now, how do I get from this angle into quadrant 2? How do I get from this angle to an angle in quadrant 2? It's really a full pi rotation. They're directly opposite of each other. So theta will equal arctan 5 over -3. You'll still have to do that. Plus pi. So the answer I would have accepted is negative 1.030 plus pi. Which, if you typed it in your calculator, would get 2.111. That's the angle. Okay? So be very careful of what you're doing when you're trying to find these angles. Make sure you are thinking about where the vector is when you're trying to assess its direction. Okay, last but not least. If the magnitude of the vector is 6 and its direction is 2 pi over 3, write the vector in component form. So here you have the option again. It all comes down to how you like to do your trig. If you're feeling not so steady with trig, I'm drawing an angle of 2 pi over 3. I mean, if you're not feeling steady with trig, drawing that angle might be the hard part. And then it's length 6 from there. So this should be eerily reminiscent of polar coordinates. And it is. It's very similar to polar right here. Nope, not that lesson yet. So if I have an angle pi over 2 pi over 3, this angle here, maybe in blue, that's a pi over 3 angle. Dot, dot, dot. And you could use trig to figure out this triangle. How do I find the adjacent side? I'm going to use cosine. So it's exactly like parameterization. Sorry, it's exactly like polar coordinates. X equals R x is always cosine 2 pi over 3. You could make a triangle here. If you find it easier to do triangle, go ahead. But most of you should find it easier to do trig at this point. Y, no, I want to drink. Y equals sine of the angle. 6 times sine 2 pi over 3. Depending on how it phrased it, you might not have to simplify at all. But 6 times 2 pi over 3 is 6 times negative 1/2, or negative 3. Sine of 2 pi over 3 is root 3 over 2. And again, the way I have that memorized is by thinking of the unit circle. Sorry, not by thinking of the unit circle. It is not by thinking of the unit circle. It's by making a right triangle in my head like this. But it's okay. So then we have 3 root 3. So the vector in its component form, my answer would have to be 3 comma 3 root 3. It's not okay to just have these two. You'll get most of the points. You won't get all of the points. That's all I have to say about polar arc length and arc length vector definitions. So, sorry, I think I hit the stop button at some point. Sorry if it's weird to be edited. Anyway, that's all I have to say about polar. Polar is done. 9.5, the wrap-up unit for BC, is how to use these vector ideas to do calculus instead of just standard vector stuff. A lot of this will be similar to that. 9.4 should be a nice homework assignment. Make sure you do the homework. If you're not doing the homework, you will fail the class. That's it. So you have a nice day. I'll talk to you soon. Thank you for your hard work. Make sure you do the homework. Bye-bye.